Hi, welcome back to this class, Evolutionary Algorithm, Genetic Algorithm. We promised to have practical implementation of genetic algorithm in part two. We had part one. Part two is about how we are going to implement this algorithm. So the algorithm used three operators, selection, crossover, and mutation to guide the searching space or to search for the algorithm until we arrive at the convergence point, then the algorithm would start. Instead of beginning from a single point, genetic algorithm uses random population to and implement those three operators so that to get a best solution or near optimal solution, we could call it. Genetic algorithm also does the binary encoding or string encoding for the variables. And we will have the flowchart, which start initialization, and then we enter the loop, evaluation, selection, crossover. Mutation is optional, and we come to it how we can use this mutation and what are the benefits of using mutation operation and then until arrive at the convergence point. If yes, then we stop, end it. If not, then continue, evaluate, selection, crossover, mutation, and in this way, in repeated way, until we get to near solutions. Now, this is the practical examples that we have. We have a fitness function x square, and x goes in between minus 4095 equal or less or equal 4095. So positive, negative 4095. That is the x values, the search space, but we don't take every single point from minus 4095 to 4095 plus. So that is the beauty of evolutionary algorithm or genetic algorithm, is that we take a sample in between, and this is kind of reduces computation complexity for us. So let's encode it. We will take 13 bits total, one bit for the sign, positive, negative. Zero is positive and negative is one. And then the other bits represent the number, the digits. So for example, plus represents zero, that zero is plus, and the whole 3,428, these 12 digits will represent the digits, and the first bit represent the sign. So here the sign is negative, minus, minus, that's one there, the first one, the first bit. So that's how and the rest, 12 bits, these are the digits. These are representing 3,428. So that's x squared. We will assume that our population is 8 individuals, 8 solutions, or we call it 8 chromosomes. And we select in our strategy the best 4 in the fitness, who get the best fitness. Those 4 will be selected, and the worst 4 will be removed, will be killed. So here in iteration initialization, we selected random values, 8 individuals. These are randomly taken, square them, and binary them. So the binary for plus 3428 is this one, and the plus is represented by bit 0, and minus 1303 minus represented by 1, and the rest 1303 represented by 12 bits, and so on and so forth. So now we select the best. This is a maximization, by the way. So maximization. So you select the best fitness. That's 11 million something. That is 1 million. So we'll take the best produced. So that is 8 million, 11 million, 7 million selected, and 8 million selected, 9 million selected. The rest will be removed. So four will be removed. Those they didn't have bigger fitness function. So now in this iteration, uh, four survived. These are the numbers that survived, and four removed, deleted. So these do not appear in the next generation. Now, population entering the second iteration, we have four selected, those the best ones, but we need more kids because we start with eight samples, eight individuals, eight chromosome, and now we have only four selected in iteration one. So to do iteration two, we need another four people, another four individuals. Now we try to bring the operator crossover to implement it. So in pair one, parent one, we have here is parent one, and we do parent pair. So this individual with that individual, and we put the crossover point. That's the crossover point, cut after 6-bit. So here literally this part with this part, this part with this part, one solution, and uh, this part with this part, another solution. So that's how we have. Now we have two solutions. Okay. Uh, Parent pair two, we do a cut after 7 bits. We said it randomly. Like you're not, I mean, we're not restricted to use a crossover point, which point we use. That's up to us to work with. So we have another 7 bits. That's here. We can, here, that's the cut. So if we take this part with this part, that's one child. Okay, that's one child. And then we take this part with this part, that's another child. So that's another two. So now we have four childs. So the population, we add them to four parents we have, and we created, we have four parents, and we created four children's from the crossover operation earlier. And now we square them, and we square them because the fitness function is x squared, fx. So now this one is selected the highest. This again selected parent. This again selected parent. This parent has less, couldn't survive, cannot survive for next generation because it's 7 million, but then there is 11 million, there is more. So this is not selected. This is selected. This is not selected, not selected, not selected. So we are looking for four people, the best four. These are the best four that we can select. Okay, that we can select. Now, here, uh, selected after, these are the selected. Removed after, I mean, these are the bad, they couldn't perform well. They were rejected. And now we are going to iteration three. Iteration three, we have only four people selected, for example. I mean, those with the highest fitness. Okay, this is selected, this is selected, this is selected, selected. So now the best four chromosome, these are the best four chromosome. Now these are the parents, and now we are trying to go get another four children. So we do crossover pair one, parent one with parent four, we cross them over, and parent two with parent four, we cross them over. So parent one with parent 4 and parent 2 with parent 3. That's how we do crossover. This is the crossing point. We choose this point to cross over to this part with this part, and this part with this part. So this part with this part, and the red with the red. So, and now we got another two children here. So the first children is this one, x3438, and the fitness square it, you'll get this one. And the second children is 3428. The first one, 3438. They're very close because the parents are close, and the crossover didn't do much change in them. So therefore, these are the kids close to the parents. Okay, so the kids close to the parents. Now, if we are doing parent 2 with parent 3, we will have the same thing. So we'll see the x is 289. I mean, this is parent 2 with parent 3, and that's the point for crossover. So this with this one, sorry, this with this part, and these with this part. So that's how we are working with them if this is the crossing points. Now, here we have the fitness for the child 4 and fitness for child 3 from the result of the crossover operations. Now here we have the result, parent 1, parent 2, parent 3, parent 4, and we got 4 children. This is before mutation. Let's do mutation. Mutation, what does it do? If crossover, like cannot change the bit, if it's the bit 0, you crossed over with the bit 1, they will just swap the spaces. But we need an operation whereby flip the bit from 0 to 1 or from 1 to 0, in maximization from 0 to 1, in minimization from 1 to 0. So here we have a random value between 0 and 1. We toss it, and if that random value less than 0.077, and I tell you why this 0.077 came from 1 over 13 bits, because the encoding we have 13 bits. So 1 over 13, it's 0.077. Now, we need to toss a value between 0 and 1, and we check it with the 1 over 30. If it's less than 1 over 30, then we change 0 to 1. Or else we don't touch it. So that's clear. So let's do for child 5. We have 13 bits. This is for the sign. Now we toss a random value between 0 and 1. For bit 1, this much, for bit 2, this much, for so on and so forth. And you can see none of them is smaller than 0.07. So the mutation cannot happen. If it's smaller than 0.07, mutation happen at that bit. So here, no mutation happen. For child 6, let's see the child 6. So again, child 6, when tossed the value are between 0 and 1, and all random values greater than 0.077. So no mutation happened for child 6. Let's do child 7. Child 7, check all bits. At bit 30 random value, well, here we found that R is 0.04, a toss value, and we found that random value 0.07. This is smaller than 0.07, 7. Therefore, we changed that bit 13 to 0 to 1, from 0 to 1, from 0 to 1. So we change it. Now you can see the small involvement happen. You see, like this one is changed. That was the before and that's the after. So the bit, the change happened. So that's change. Now, child 8 before it was this one. Suppose crossover produce near optimal, bit 13, check mutation, and now we receive R again, 0.04 less than zero point 0.7. We do the again we do the flipping. So once the idea of flipping, that we want to get 1 1 1 1 1 1 1, a solution of 1 1 13 bits. It means that if this is squared, then you get the maximum fitness. And that's the idea. Without mutation, you can't do that. So that is maybe the optimum, 16 million. That's 16 million. That you see all of them became 1 1 1 1. Crossover cannot make crossover between two chromosomes, two solutions, can't give you all ones or all bits are zero. Cannot. So therefore, mutation comes in to help you, to support you, to get optimum solutions. Why mutation? I explained it, because without mutation, you can't get all bits, best possible chromosome, which are all ones. So if this is, for example, if this is your solution, no matter how you can do crossover, the ones and zeros still, they'll be same. So the mutation will flip this one into one. So flip this one into one. It changed it to one. So that you get the highest value. Thank you very much. Stay tuned for more algorithms on evolutionary algorithms. Thank you very much. Take care.